Patrick, and I guess for the last few years, I've been looking at how the amount of nutrients at the ocean surface is impacted by tidewater glaciers in Jones Sound, Nunavut, which is near Ajuktatuk or Grise Fjord, the location of the forced resettlement of Inuit families from Inukjuak, Quebec in 1953. And just as a white settler working in Nunavut, I think it's important that we recognize the continued impacts of both past and present forms of colonialism in the North, as I'm discussing glaciers and the waters around Tularotit. So, tidewater glaciers are glaciers that terminate directly in the ocean. And recent studies around Greenland, Alaska, and Svalbard have shown tidewater glaciers to be important zones of productivity, right? So they find elevated concentrations of phytoplankton, the photosynthetic primary producers at the surface near these glacier termini. So potentially stimulating the base of the Arctic food web, which can in turn go on to stimulate secondary producers and then potentially higher trophic levels as well. And so these studies suggest that glacial melt, which is released at depth and then rises as a buoyant freshwater plume, is somehow stimulating this productivity distal to tidewater glaciers. And this increased photosynthetic productivity has been linked to the delivery of nutrients. Here we're talking specifically about the bioessential nutrients nitrate, phosphate, and silicate. And in the summer, in the Canadian Arctic, nitrate is the major limiting nutrient at the ocean surface. So these nutrients could be delivered downstream directly in glacial melt, but additionally, the buoyant freshwater plume as it's rising through the water column can also entrain nutrient-rich deep water via upwelling. And so depending on the geometry of the glacier in question, surface nutrient availability differs, right? So models in Greenland suggest that there's kind of this productivity continuum between land terminating and tidewater glaciers, with more productivity at glaciers that are grounded deeper, right? So around 580 meters below sea level, and decreasing as glaciers become more shallow. And so just to kind of see what that looks like, in a productive scenario at a deep tidewater glacier, fresh water is released at depth as this plume. It rises because it's fresh water, right? It's less dense than the surrounding salt water. And then on its way, it's dragging at the surrounding salt water. And the result is that it pulls deep water, this plume pulls deep water up with it, bringing nutrients to the surface. As glaciers retreat and transition to less productive land terminating glaciers, the strength of this upwelling declines, right? So turbid meltwater is released directly at the surface, which limits light penetration through the water column, and then also creates a more stratified, less well-mixed water column. And to date, most studies have focused on these end-member glaciers, with a few studies exploring tidewater glaciers discharging at depths really less than 100 meters below sea level. And with continued glacier retreat, understanding these intermediate systems is super important. Specifically, the Canadian Arctic is understudied when it comes to glacier-ocean interactions. The last formal published study was put out nearly 50 years ago. And so our lab works to answer some of these questions about glacial mediated nutrient availability in Jones Sound, Nunavut. You can see in this satellite photo, there's this light colored area of water, right? This plume right in front of this glacier. So this plume draining off of Sverdrup Glacier. And it's in this plume where productivity may be higher. And so in our discussion with the HTA of Grise Fjord, several glaciers around Jones Sound were identified as areas of heightened productivity and also important hunting grounds. And Sverdrup Glacier that we're discussing right here is the subject of this study. Before we go there, though, we kind of got to iron out a couple questions. Three main questions came up in our conversations about nutrients, glaciers, and Jones Sound, namely, can a small tidewater glacier export significant amounts of carbon and nutrients to the ocean? can this discharge from a shallow tidewater glacier still induce the upwelling that we've seen at larger glaciers, bringing nutrients to the ocean surface? And then finally, how might productivity change with more or less glacial melt, kind of in the context of global climate change? So yeah, as I said, my work focuses on sphere drop and using nutrient and water data collected aboard the Vagabond, this boat pictured here. We can measure how glacial melt moves through the ocean in front of sphere drop. And today, I'm going to be focusing on some data that follows this purple line. So kind of starting within couple hundred meters of the terminus and then extending out almost 25 kilometers into Jones Sound. And so our first question centered on whether or not glacial melt is directly contributing nutrients to the ocean. This is just a table of nutrient concentrations, both in fresh water, so in green, and then marine water below that. And you can see that that concentrations are much higher at depth, right? So these in this blue box for nitrate, phosphate, and silicate. Moreover, if we look at just the upper 40 meters of the water column, near surface marine nutrient concentrations are either lower or within the error of on ice freshwater concentrations. And what this means in terms of, I guess, direct addition of nutrients from glacial melt, it means that sphere drop, in order for it to be solely responsible for surface nutrient concentrations seen in the ocean, it would need to be exporting volumes of melt several orders of magnitude more than it currently does. So the nutrients at the ocean surface cannot be due to glacial addition. So moving along into the ocean, in this graph, we're looking from left to right from the terminus of sphere drop out into Jones Sound, right? So starting at close to the terminus, working our way out. And then from top to bottom, we're looking at water depth from the surface down to about 60 meters below sea level. Colors here are representing water density. So deep water, denser water in yellow, lighter, fresher water in purple. And we see that there's this kind of this hump of denser water close to the surface, right? These upsloping isopycnals that we're looking at here, showing that deep water is being brought to the surface close to the glacier terminus. And as glacial melt is entering the ocean, and at sphere drop, it's entering the ocean around 30 to 40 meters below sea level, it's rising to the surface and it's dragging this deeper water with it, right? Creating this upsloping structure. In this plot, still looking at distance from the glacier from left to right, depth from top to bottom. The white lines are showing the density lines of the last graph, but here color is looking at nitrate concentrations, right? The limiting nutrient during the summer in Jones Sound. And so areas of yellow have more nitrate, areas of purple have less, and there's more nitrate at depth as expected, but also near the glacier where, again, we have these areas of upsloping isopycnals, we also have areas of heightened nitrate concentration close to the terminus. So even though sphere drop's not directly adding a lot of nutrients in glacial melt, it is bringing deep water nutrients up to the surface for phytoplankton to use during the summer. And we can measure that. So this plot, again, distance from left to right, depth from top to bottom, white lines showing the isopycnals. But here color is the amount of chlorophyll A, so the green part of phytoplankton. And we can use chlorophyll A as a proxy to just measure concentrations of the phytoplankton communities in the water column with these organisms right at the base of the food web. And here, yellow, more chlorophyll A, blue, less. And once again, we see that there's more chlorophyll A both near the terminus of sphere drop, but also in this area of upwelling, in this area of upsloping isopycnals. So where this denser deep ocean water has been brought to the surface along with glacial melt. And so if we just want to circle back to our original questions, question one, can a small tidewater glacier export significant amounts of nutrients to the ocean? Short answer is no. The concentrations in glacial melt are going to be too low to directly augment downstream concentrations. It's what that water is doing in the ocean and how it's perturbing the water column in front of the glacier that matters here, right? So this upwelling? Can discharge from a shallow glacier still induce upwelling and bring nutrients to the ocean surface? The answer is yes. We have the density profiles are showing that there is upwelling starting at around 30 to 40 meters in depth, close to the terminus. There's also elevated nitrate concentrations in this deeper upwelled water. And then finally, this question of how are primary producers impacted by the plume, and then how might productivity change with more or less glacial melt. And so far, we only have 1 year of data, so answering this question of change is difficult. But we do see higher concentrations of chlorophyll A in areas of glacial upwelling. And so as glaciers retreat, the depth that glacial melt is entering the ocean is going to change. And so in the short term, more glacial melt exiting at current depths might actually force more deep water to the ocean surface, which could theoretically help productivity, right? It's pushing more nutrients to the surface. But that being said, as glaciers retreat, they can transition to land terminating glaciers, and productivity could ultimately decrease. All that really to say that continued monitoring is necessary to better predict how the food web of Jones Sound is going to be impacted by glacially mediated nutrient availability. There's only a year of data, and we're going to continue to keep looking. And I think with that, I need to thank my field partners, my collaborators, the folks up in Grise Fjord who made all of this work possible. And I will happily take some questions if there are any. So yeah, thank you.